Okay, it says that we are recording. And Jim Sanford, I'm going to turn it over to you, and I will mute my mic, and you can take it from there.
Okay, thanks, Glenn. Good evening, everybody. This is WB4GCS Jim. This is part two of a two-part series on the Smith chart. Um, Last time around, I presented a discussion of all the ugly arithmetic that could be solved graphically with a Smith chart. And my goal tonight is to show a little bit how you can actually use a Smith chart, and more importantly, how you can use some software to use a Smith chart even easier than what I learned at the Naval Academy back in the 18th century. Um, so that is the goal here. I would like this to be an interactive discussion. So if you have questions, throw it on the chat. I will try to look for it, or just unmute your microphone and throw me the question. I would like it to be a discussion, not just a lecture from me. And I am fully expecting to take away homework assignments of questions that I can't answer tonight. Um, and then I will find some vehicle to get back to everybody about this. So the biggest thing is number one, I'd like to have one conversation. Number two, I would like everyone to be heard. And number three, I want it to be a discussion. So don't be shy if you have questions. First off, can everybody see the title slide on my presentation? Let me ask it this way. Can anybody not see the title slide?
I can see it.
Okay, good. I'm gonna take that as everybody can, and okay, I wrote the presentation, but I've given Larry credit here because he has done a lot of work with the software that I'm going to talk about and some of the applications that we've talked about, and quite frankly, his work was part of what inspired me to put this discussion together. I will say up front that, oh my God, the Smith chart is very intimidating. And I'll show you one, and it looks pretty complicated. But as we explain it, I think it'll make sense. And the way to look at the Smith chart is a graphical representation of some ugly mathematics on impedance matching. You've got a load impedance, you've got a transmission line. What's the impedance at the front end? The Smith chart will help you graphically deal with that. And then when you roll in with the software, it gets really easy to use. And you can both iterate things and say, well, let's go try this. But I'm also going to show you some things that'll tell you, well, here's how to develop a strategy so that I'm not just guessing. Here's based on what I've got. Here's my strategy of what I'm going to do. And one of the end objectives in mind is, we probably, most of us have antenna tuners. So we take the antenna, we take a piece of coax, we hook it to the radio, and we use the antenna tuner to make the radio happy. But one of the big questions is, yeah, what's going on in the coax? And can we do something at the antenna to make life better in the coax? And by better, I would say lower peak voltages that might smoke the coax and lower loss. So that's kind of the high level objectives of what we're talking about. And now I am going to try to turn my camera off to again save bandwidth. It's not letting me do that. Sorry. All right, so I just changed to the slide of references. Can everybody see the references slide? Can anybody not see the references slide? Okay, I'm going to take that as everybody can see it. So I rearranged these. These are the same references I used in my last presentation, but I rearranged them in order of which I think you might find them usable. The first one is the self-paced essays, which is a series of articles by Eric Nichols, KL7AJ in QEX. It's a 3-page high-level summary of the Smith chart, and that'll get you started in an introduction. The next reference is Yu, Coax, and Smith, How to Draw and Use a Smith Chart by Michael Toya, K3 Mike Tango. And it's only $14 on Amazon, and that price is based on what I looked at today. And what I find most useful about this reference is it's very intuitive, and it tells you how to start with a clean sheet of paper and create a Smith chart. And I will tell you, I learned how to use the Smith chart in 1970, whatever, at the Naval Academy. And I always wondered, okay, how was that generated? This book tells me how to generate it, how I can create it. And so if you read no other reference, I would suggest you go there. And obviously I have it. And if anybody wants to borrow it, that's fine, but I'm going to want it back. The next reference is Antenna Impedance Matching by Wilfred Karen, published by the ARRL in 1989. And if you look, you see there's a whole lot of orange stickies in my copy. And basically what it is a bunch of examples of using the Smith chart to take a set of impedances that you have at the antenna and match it to something your transmitter will like. And one of the things I find most interesting in that book is the last and most complex example is matching one antenna over the range of 2 to 6 megahertz. And if you think about it in terms of octaves or percent, that's a big broadband challenge. And it's not a simple L network. There's a bunch of stuff, but there's a bunch of really good examples in that book. And again, I have it. Anybody wants to borrow it, you're welcome to, but I'm going to want it back. And I will share that some of you know I spent a long time in the Navy, and on Navy ships, our transmitting antennas tend to be 2 to 6 megacycles, 6 to 10 megacycles, and 10 to 30 megacycles. And so they're pretty broadband, and the antenna tuners that couple a transmitter to that antenna are designed to handle that. And I will tell you that we feed multiple transmitters into a single antenna. Okay, what about receiving? Well, we use separate antennas for receiving, and that's a whole different story. The fourth reference is an article called Smith Chart Calculations. It's out of the ARRL antenna book. Here it is. And, where it's going to be is going to vary with what edition, but it also provides an intuitive description of what the Smith chart is and how you can use it to avoid some really ugly trigonometry and mathematics. The fifth one, and I've got this in bold because this is the primary reference, is this is a book by Phil Schmidt. He developed He developed the Smith chart in the 1930s. And this book was published in 1995 and again in 2000. And again, you can see I have a whole lot of yellow stickies and tabs on it. It is more detailed and less intuitive than some of the earlier references, but is certainly understandable by anybody smart enough to get an amateur radio license. As an example of using the Smith chart, reference 6 is a simple broadband dipole for 80 meters. You know, 80 meters, if you look at the fractional bandwidth, 3.5 to 4 megahertz, that's a pretty significant broadband bandwidth. How are you going to get one antenna to match all that? And there are various ways people can do it. And I talked about some of those ways in my earlier presentation. Um, but Frank Witt talked about ways of using coaxial feed lines of different impedances to broaden it out. And then in the next reference, Dave Leeson in QEX did a discussion on how to do that and how it works. And I'll talk about that. And Glenn, if I don't talk about how that works at the end, slap me around and make me come back to that, please. Um, kind of related, and I referenced it more in my first presentation, but I talk about it a little bit here, is the Amateur Radio Vertical Antenna Handbook by Captain Paul H. Lee, U.S. Navy, retired. He's long since silent key. That was the book that got me to stop avoiding vertical antennas. And the fundamental issue there was he made the point that it's easier with a vertical antenna to get a low angle of radiation for DX than it is to put up a dipole high enough to get that same low angle of radiation. And I had always avoided vertical antennas because of the pain of doing radials. And he's got some information in there, and there's some other references that talk about radials. And I've read a whole bunch of research on radials. It would be the subject of a separate topic, separate discussion. But the bottom line is the more radials you have, the less anything else matters. How many, how long, whether or not they're resonant, whether or not they're on the ground, in the ground, or elevated. The more radials you have, the less anything else matters. And Frank N3FB keeps reminding me that I kind of demonstrated that because for years I worked a whole lot of distant conversations, including regular conversation with folks on the East Coast on 75 meters, using a 35-foot vertical that Glenn gave me till a windstorm destroyed it, and the radials were dog fence wire. You know, broadcast stations have to put down 120 radials of number 10 wire, quarter wavelength, and what I have learned in my research and in my limited experience is the more radials you have, the less it matters. At one point, I built a cage vertical with 16 radials on it that were very asymmetrical because of the shape of the property. And when I called a friend of mine in Northern Virginia, his response was, "My God, you're the loudest signal on the band." And when I put up the vertical that Glenn gave me, I put down 36 radials of dog fence wire of varying lengths. And the guys on the East Coast could hear me only running 100 watts. And probably because of the length of the feed line, I was probably only getting 70 watts to the antenna. Today I work them with an NVIS dipole running a kilowatt. So that's the point of that reference. And if you're at all curious about vertical antennas, I would encourage you to look for that book because he has a bunch of different examples. And well, that's the point, examples. Reference number 9, antennas, second edition by John Krause. John Krause is the antenna expert, and he came up with what do we call it? Looking for satellites and stars and all that. There's a lot of calculus and mathematics in it. So I would not encourage everybody to go buy that and read it. But if you want to get into the basics of things, that's the place to go. I have read that book cover to cover twice, and every time I pick it up and look at it, I learn something. Reference 10 is by a former ham. He's now Silent Key, Jack Layton, W9 UK. He used to tune directional antenna arrays for broadcast stations, AM broadcast stations. I learned an awful lot from his book and from just talking to the man. And then most recently, I read an article. Jack was a fan of shunt fed dipoles, and that's where I'm sorry, shunt fed verticals. And that's where the vertical is grounded. And you run a parallel feed line, you run a parallel wire up to it on the top, and then you adjust that connection down until the thing is slightly inductive. And that's how you match the antenna. And it has the advantage of everything is a DC ground, and you don't have to mess around with all this garbage that other AM broadcast stations have to do to isolate all the other feed lines and power lines for lighting, everything else going up the tower. The base of the tower is at DC ground. The entire tower is at DC ground, and I'm a fan of that, and I'm heading that way on two different antennas, one being my 110-foot tower for 160 and 80 meters, and the other one being a 43-foot vertical from DX Engineering that I'll use on the higher bands. Because one of the things Jack pounded into me is your tower is too tall for 40 meters. So, okay, I got the message. And then the last reference is instead of making that shunt feed some distance parallel from the tower, if you flare it out into a triangle, you're going to get higher bandwidth. And that has advantages. One of the things Jack told me about was KDKA, when they went to their digital transmitter, they had trouble with SWR trips because their half-wave vertical dipole was so high Q that it could barely handle the bandwidth of the AM modulation and forget about the bandwidth of the digital. So those are my references. And like I said at the bottom, I rearranged them in the order of perusal if you wish to learn more. I would call number 1 and 2 the most important if you want to learn more about the Smith chart and impedance matching. Okay, so some basics from the last time that I wanted to review. We work in 50 ohm systems and would like to match to 50 ohms. We need to keep in mind that impedance is a complex number that expresses resistance and reactance. Resistance is like a resistor, and that's what does real work in our antenna situation, radiates power. Reactance creates circulating currents. And it doesn't help us with what we want to do, but it is something we need to deal with. And resistance can be expressed in 2 ways. There's the Cartesian or rectangular coordinates, where the impedance is expressed as resistance plus J times reactance. Okay, what's J? Square root of -1. Well, that's an imaginary number. It doesn't exist. But mathematicians and engineers find that concept very useful for expressing things like impedance. Another way to express impedance is a magnitude at some angle. And the magnitude is the square root of the impedance squared plus the reactance squared. And the angle is the arctangent or the antitangent of reactance over resistance. Why express it 2 ways? Well, in my days at the Naval Academy with an HP calculator, you can add impedances with R plus JX very easily, but if you want to multiply or divide, the angular expression becomes easier because you just multiply or divide the magnitude and then you add or subtract the angle. So there are reasons for both. And on the calculator I used at the Naval Academy, you could push, you could enter resistance, you could enter reactance and push one button and get the polar form, and vice versa. But one of the most important things in this talk is the fact that impedance is a complex number. It's resistance and reactance. We often think in terms of 50 ohms. Well, not so fast, especially if you're looking at an antenna. Or for that matter, a power amplifier. And that's another subject for a different day. The manufacturers work to make the transmitter impedance 50 ohms resistive. And with solid state devices, the way they match those things, it's very broadband as opposed to like my SB220, which I have to tune if I move 200 kilohertz on 75 meters. But most of us are running solid state radios, which the manufacturers have designed for 50 ohms. But that means that transmitter wants the antenna to be 50 ohms. And that's not always the case. And if you really dig into the theory, Krauss's book or the ARRL antenna handbook or even the ARRL handbook, at resonance, at perfect resonance, a vertical antenna is going to be around 37 ohms. That's not 50 ohms. And a dipole is going to be 73 ohms, not 50 ohms. And I did some arithmetic today, and the SWR is going to be between 1.1 and 1.2. And okay, the internal tuner in most radios can deal with that. But if you're running 1500 watts, you might want to think about that. Now, another concept that's important is admittance. And that's given the symbol Y, and notice it's bold because it's a complex number. And that's 1 divided by, I said R, I should have said impedance, sorry. 1 divided by the complex number of impedance. And, that's for many people a difficult concept. And I will tell you it was a difficult concept for me until I figured out. But if you look at the equation for parallel resistors, 2 resistors in parallel, the resistance is 1 over the sum of 1 over R1 plus 1 over R2. Well, guess what? 1 over R1 and 1 over R2 are the admittance of the 2 resistors. And then 1 over that gets you to the resistance. So bottom line here is when we are putting resistances or when we are putting impedances in series, we just add them. When we are putting impedances or reactive inductors in parallel, life is easier if we deal in admittance. And I'll show you how to do that. Again, I'll show you how to do that graphically without the ugly arithmetic. Any questions so far? Okay, so here is a way of looking at complex impedance, and this is a broadband look of a VHF antenna. And what you see on the horizontal axis is resistance, and on the vertical axis, you see the reactance. Positive reactance is inductive, negative reactance is capacitive. So this particular antenna is around 50 ohms at something above 125 megahertz, but it's also got 50 ohms of reactance. So we might want to do something about that to get the maximum power transfer. Here's the Smith chart, and everybody's head's going to explode. I will talk through this. This is a circular way of looking at those reactive coordinates. And again, it was the coax, here it is. It was the coax U and Smith charts book that helped me understand this. I mean, I learned 50 years ago how to use a Smith chart, but where the heck did this come from? Well, it's actually pretty simple. The far right end is, well, first of all, the horizontal line in the center is pure resistance. The far right end is 0. The far left end is infinity. And so you see a bunch of circles here that are tangent to the far right end. Those are lines of constant resistance. And then you see these other circles that are tangent to the horizontal line. And, the perfect world would go off here to be a full circle, but we don't need them. Those are curves of constant reactance. So given a complex impedance of an antenna, you can plot the resistance and the reactance on this chart. Say here. Oops. And so let's say here. And then you can use these circles to add series reactance to get the impedance up to the one line. What's the one line? Well, to use a Papersmith chart, we normalize the impedances. So we measure the impedance of the antenna, we divide it by the system impedance, usually 50 ohms, and that gives us a small number. And the idea and a perfect match is at 1 ohm, 1 normalized ohm plus 0 reactance. And now this particular paper has been normalized for 50 ohms, so it reads 50 instead of 1. What I learned was this point would be 1.0. So you can plot any impedance, and then you can figure out how to use series reactances to get to a resistive impedance of 1. And I said admittance is the inverse of impedance. So the red lines on this chart are impedance. The blue or green lines are admittance. So if, for example, I'm going to use a series reactance, I would move along a red line of constant resistance. If I'm going to use a shunt reactance, I would take the inverse of the impedance, which is diametrically opposite, same radius from the center, but over on the other side, and I would move along a line of constant admittance to get to where I can move on a constant resistance to get to 1.0. And I know that probably makes your head hurt, but the arithmetic I showed last time would make your head hurt even worse. And you do this a few times and look at some of these references, and it will make sense to you. I am willing to work in admittances when I need to. I don't like this chart because it's a little bit busy for me. And we're going to come back to a way to deal with that easier here in a few minutes. So here's where it gets practical. We can easily measure the impedance of the transmitter, right? We've all got our Rig Expert or our MFJ device or a network analyzer or whatever. But we would really, in a perfect world, like to learn what's the impedance at the antenna. Well, the first thing you need to know is the electrical length of the feed line. And there's a couple ways to get to that. You can go measure the physical length of the feed line. That may be inconvenient if it's already in place. And then multiply by the velocity factor, which may or may not be accurate because my experience is published velocity factors are not always fully accurate. But you can also use a Rig Expert or a network analyzer or a nano VNA, any of these cheap devices, and you set the velocity factor equal to 1 and measure the length, and that's the electrical length. And that's what we care about. We don't care about the physical length. If we're going to get into attenuation and loss, well, we care about the physical length, but for the purposes of that, of matching impedances, what we care about is the electrical length. Now, an important fact that most of us probably know, but may not understand as profoundly as we should, is antenna impedance in coax is repeated. So the impedance at the antenna on a piece of coax, a half wavelength toward the transmitter or a wavelength toward the transmitter or 1.5 wavelengths toward the transmitter or however many multiples of the half wavelength will be the same. And if you plot an impedance on a Smith chart, one circle on the Smith chart is a half wavelength. And I don't care if your coax is a half wavelength long or 50.5 wavelengths long. You rotate on the Smith chart that many times. And if you know it's 50.5 wavelengths long, you only need to go a half wavelength and you'll have the same impedance. So that is a profound fact that using the Smith chart to visualize impedances will help us all understand. And on the Smith chart, if you plot an antenna impedance and you rotate counterclockwise, some number of degrees, some number of fractions of a wavelength, you will have the antenna impedance at the antenna. And notice it says toward generator. Okay. And the Smith chart tells you this. Toward generator is counterclockwise. If I know the antenna impedance and I want to know the impedance at the transmitter, I would rotate clockwise. But in my experience, most often we can measure what I've got at the transmitter, but I want to know what's going on at the antenna. And that leads to the question, okay, why do we care? And my answer is we may decide we want to do something at the antenna. Okay, why is that? Well, there are charts. Yeah, don't have them here. It's in my last lecture. If you have an impedance mismatch, you are going to incur additional loss in the coax that you wouldn't otherwise have if you matched the antenna at the antenna. So the idea being you may want, and I emphasize may, you may want to match the antenna impedance to 50 ohms at the antenna. One reason is that additional loss. Another reason is if you're running 1500 watts, that additional loss is going to generate a whole lot of heat in your coax. And gee, I wonder how long that's going to last. So that's why we might care. And the Smith chart, the tools we use to measure impedance at the input to the feed line and the Smith chart may help us assess what's the impedance at the antenna and then make a decision as to whether or not we want to do anything at the antenna or live with what we've got. And in a case of living what we've got, I've got this random offset center fed dipole with a 4-to-1 balun on it that I threw up 20 years ago to get something in the air and something on. And I'm learning as I spend more time on 75-meter nets and as I work military stations on the West Coast and in the Gulf. That antenna works actually a lot better than I ever expected it would. But it definitely needs a tuner. And I will be looking into, all right, is there something I can do at the antenna to broadband it? That's why we care. We can easily measure what we have at the transmitter, but we might want to know what the impedance is at the antenna, and then we can make a decision as to whether or not and what we're going to do at the antenna. You may not need to, but it would be good to know. So moving on the Smith chart, as I said a minute ago, impedance repeats itself every half wavelength in a feed line, and that's one circumference around the Smith chart. Admittance is diametrically opposite to impedance on the Smith chart. If you're using a paper Smith chart, you plot the normalized impedance, and then you take a straight edge and take that through the center, and then a set of calipers like my Naval Academy navigation kit, and go the same distance on the other side, and you now have the normalized admittance of whatever the load is. And again, the value of transferring to admittance is when you put things in parallel, admittances add. If you're dealing in impedances, combining parallel loads, that's some more ugly arithmetic that I'd rather not.
Hey,
Some other,
Jim,
yeah, go ahead.
um, I tried to message you, but you didn't hear me or see it. On the first bullet point, impedance repeats itself every half wavelength on a feed line. Um, is that is that affected at all by the velocity factor of the feed line?
Yes, it is. It's okay. Good comment. I should insert into this every electrical half wavelength in a feed line.
Okay,
So
thank
the
you.
velocity factor definitely does matter.
Okay,
Thank you for the question, Glenn. That was a good one. Okay, so moving on, series capacitance moves the impedance counterclockwise along one of those circles of constant resistance. So if I add series inductance to an impedance down here, it's going to move me this way. Series capacitance will move me counterclockwise this way. Parallel capacitance in shunt moves the admittance point clockwise on a circle of constant conductance. And if you think about admittance and admittance being the inverse of impedance and conductance being the inverse of resistance, that makes sense. Parallel inductance moves the admittance point counterclockwise, again on a circle of constant inductance. And these are powerful things to know that we can use to develop matching circuits either on a paper Smith chart or electronically, as I'll get to. So here's an example of an L network. There are 8 possibilities of an L network. You see series inductance and shunt capacitance and so forth. And in this region, that network will get you to your reference impedance. Down here, that's the forbidden region. Forget it. The arithmetic doesn't work. But down here, where's my mouse? There you go. Down here, a parallel capacitor and then a series inductor. Notice the capacitor is up front instead of downstream. Will get you there. So with these two circuits, you can match any impedance. And there are other variations thereof. Now, what I like about these two circuits is they are both effectively low pass. And you could make the argument that, okay, your transmitter has a low pass filter in it. And yeah, okay. And your amplifier should have a high Q output circuit and attenuate harmonics. But if you're doing your matching with one of these two topologies, you're getting additional attenuation of harmonics. So I'm a fan, and this is an opinion, guys. This is not a fact. This is an opinion. I'm a fan of these two circuits. And as you see in the graphs here, with one permutation or the other of this low pass topology, you can match anything. And I got these graphs out of this book, the Wilfred and Karen book on impedance matching. I would have expected to see something like this in the ARRL handbook or the ARRL antenna book, but could not. But that's okay. We'll get to how to handle this if you're not sure. Here's some other significant notes. A shunt capacitance moves high frequencies more than low frequencies. A shunt inductance moves low frequencies more than high frequencies. A series capacitance moves low frequencies more than high, and a series inductance moves high frequencies more than low frequencies. And these facts can be useful in determining which topology you want to use when you have multiple options. More importantly, um, this can be useful when you're trying to match a given antenna of a certain impedance range to, let's say, an acceptable SWR. And the Karen book that I just showed you has several examples of that. And like I said, the last one and the most complex one is matching one antenna uh, to an acceptable SWR on a range from 2 to 6 megahertz. And that's hard, but it can be done. So these fundamentals are worth remembering. And I do intend to make this presentation available somehow on the website. So, and you know, Glenn's doing a recording. So you don't have to memorize these tonight, but I just, if you walk away with nothing else, walk away with these important principles. So I've been alluding to, there's an easier way to do it. You know, the Smith chart lets us do this stuff graphically. There's an easier way. There's a couple of free programs out there. One is called Winsmith, which I used years ago and have forgotten how to use. Another one that's more up to date is called SimSmith, although in a recent update, he renamed it NextSim, as in Naval Electrical Code, where he is, if you're familiar with LNEC and EasyNEC, NextSim incorporates a front end like EasyNEC to the NEC algorithm, which was developed by one of the federal laboratories, and then gives you the graphical output to see what you're doing. And what it is a program to graphically do what we're talking about without some of the ugly arithmetic. In fact, I talked earlier about how typically on a Papersmith chart, we normalize the system impedance, which means we divide what we have measured by the system impedance. Well, guess what? The software does that for us. And it has been greatly updated recently. And here's where to go get it. And along with that, in the help file is some excellent documentation. And I would encourage you to go get this program and read that documentation, whether or not you're going to ever use it, just to help you understand what we're talking about. Now, there's another guy that has a bunch of YouTube videos out there, and they're very good, but they're based on older visions of what we used to call SimSmith. I'm going to show a more challenging example that Larry did. Okay, and now it gets funny in terms of what I want to present. So here's a simple example. Let's assume we have an antenna that has an impedance of 50 minus J10 ohms. That means its capacitance at the center of the 75 meter band. Normalized, this is 1 minus J.02. And it's pretty obvious that we can match it with a single series inductor. And that's why I chose this example for simplicity. It'll be relatively narrow band, but it works for this example. So we plot the normalized values on the Smith chart. We are already on the resistance line 1.0. We just need to see how much series inductance is required. So we rotate clockwise on a line of constant resistance to the center of the chart. And then we see we need to add 0.2 normalized ohms of inductive serial impedance clockwise. And okay, so that's nice. How do we get to the inductance? Well, first we need to denormalize it, which means multiply it by system impedance. And then you probably all remember, you know, X sub L is 2 pi JFL. Well, you do some algebra and L becomes 1 over 2 pi JF. And so you do that calculation, and now you know how many microohms or milli ohms you need. And more advanced example, there was an article in QST and then in QEX a few years ago about how to broadband an 80 or 40 meter dipole. And um, you can do this on a Papersmith chart. Um, to do it, you have to do the normalized impedance and then renormalize to a different impedance and then denormalize back. And it can be done. I have done it. It's complicated. It's convoluted. Um, and we'll talk shortly about an easier way to do it. SimSmith makes it simple, and I'll show you how and why in a few minutes. And from the most recent article about doing this in QEX for November and December, I should have written that in here, November and December of 2018, here's an unmatched 80 meter dipole. And here's a 80 meter dipole with the wideband technique we're going to talk about. Okay, so now I need to bear with me a minute. Okay, can you see my polar plot?
Yes.
Okay, good. So this is the simple example where I talked about. So you plot R plus JX, and you see I'm on the one ohm resistance line, but I'm not at zero reactance. And so I move to get. Thank you very much. So I move to the zero reactance line, and on a Papersmith chart, I have to look at, okay, how much normalized reactance am I adding from here to here? But and this is a peek into the SimSmith software. All I did to create this was move the mouse wheel. I clicked on here, I moved the mouse wheel until I got to where I wanted to be. And you see my circuit. I've got the load impedance, I've got the series inductance, I've got the generator, and Sunny Beach, I'm at a 50 ohms and an SWR of 1.03. So that's why I say this software makes things easier. Now, I built this circuit. The load is 50 ohms. The reactance was minus 20. The program normalized it for me. And I decided, okay, I'm going to use a series inductance. And so what I did was I dragged and dropped a series inductance in the circuit. And then the program tells me, okay, here's my resistance and SWR at the load. Here's my resistance and SWR at the other upstream side of the inductance. And I look at the source and I'm looking at an SWR of 1.003, when here my SWR would have been more like 1.5. Now, I admit we could all live with an SWR 1.5. I get that. I was trying to keep this example simple. But a couple of key points I want to make from this. You know, we are used to thinking of signal input thingies and output left to right. And this program works load impedance, thingies, and generator left to right. Why is that? Because in my opinion, if you think about this as a process and not a signal, the process input is whatever we got at the antenna. And then we're going to do whatever it takes to make it match, to make the load, the user, happy. So that's, in my opinion, a rationale behind the way this goes left to right. And in terms of drag and drop, you see you got all these components. You got a series capacitor, parallel capacitor, series inductor, which I used, parallel inductor, which I can just drag and drop. That's going to screw things up, and then I can undo that. And you can also do an open stub, which people have written about in QST, a series stub, or a series parallel stub, which people have written about in QST. You can use, series resonance circuit, a series resonant shunt circuit, a more complex circuit, all this stuff you can drag and drop. And these things with the funny names down here are where you build more complex networks that the documentation talks about. But the point is, you can start with a load, you can start with a generator, and you can start putting stuff in there. Now, you could do this randomly, but if you go back to here and develop a strategy, this tells me that I need a shunt reactance on an admittance circle and then a series reactance on a resistance circle. So by keeping these things in mind, and I wish to God the ARRL published them somewhere. And like I said, we'll have this published. And if I find a cleaner presentation, I'll make that available. This knowledge allows you to develop a strategy to deal with how I'm going to get from an impedance, say here, around to where I want to be, which is 1 plus J0. And that's the object of the exercise. And so this software lets you drag, you develop a strategy based on the previous display, and then you just start building it and experimenting with it, and you'll see as you add things, and you don't have to calculate these values. Click on where you are and roll the mouse, or I'm sorry, use the mouse scroll, the mouse wheel. That's the word I'm looking for. And you can move it until you get the answer you want here. And instead of having to denormalize the change in impedance and then use the 1/2 pi FL to get the inductance, the software is telling you the inductance. And now the geek in me would like to know the impedance or the reactance. And I had a correspondence with the author of this software, and we discussed that issue. And he said, look, display area here is small. So this is the bottom line. How many nanohenries do I need? And he chose to display the bottom line and not the reactance, which really would be extraneous information. So I could not argue with that. So this software does a whole lot for you pretty intuitively. And you can play. You can add it, you can add a component in the circuit here, and then if you don't like it, you can delete it like I did a few minutes ago. So that's the value here. So back to the presentation. Here is the website where you can get that software, and whether or not you're going to ever use it, I would encourage you to get it, install it, and then go read the help file. It'll tell you an awful lot about impedance matching in a very intuitive way. And as I mentioned earlier, there's some YouTube videos out there by KE0 somebody or other, but they're based on much older versions of the software, so I didn't find them as useful. Now, Larry and I have talked about a more challenging example, and that's this one where we've got a single dipole antenna. That's a simple example, sorry. We've got a single dipole antenna that we would like to broadband across 80 meters. The entire band. This is what you get with a dipole cut for 3650. This is what you get if you broadband it with a certain technique. And that technique, bear with me. That technique involves a one wavelength piece of 50 ohm coax and then a half wavelength piece of 75 ohm coax. And when I first read that article, I said, what the heck is the point of one wavelength of 50 ohm coax? Because the impedance is going to be the same. We will come back to that. That's something Larry discovered. Um, the, the half wavelength of 75 ohm coax, it turns out, is inductive where the antenna is capacitive and is capacitive where the antenna is inductive. So it tends to bring things down closer. Not perfect, but better. Now, I will tell you 40 years ago, I used a similar technique to match 75 ohm cable TV hardline that was free to a 50 ohm antenna and a 50 ohm transmitter, and worked pretty well. Where we failed was when we tried to broadband it to cover 10, 15, and 20 meters. That wasn't going to happen because it's based on the wavelength. But if you've got a single band antenna and you want to broadband it, this is a valuable technique. And how to do that is in one of the references that I cited at the very, very beginning. Actually, there's two references to talk about it. Go ahead, Glenn.
When you have those lengths, those are not insignificant.
I'm sorry, I can't understand you.
Those lengths of coax,
Yes.
they are not insignificant. So could they simply be coiled up, or do they need to be run across the ground somehow?
Well, funny you ask that. Because as Larry learned, and that's why I gave him credit in the title page, is Larry did some experimenting and playing with all this and figured out that, well, part of what does what we want here is the loss in this one wavelength of coax. And okay, you could argue the guy's cheating. Well, maybe not. You're going to have loss in the coax anyway. So rather than ignore it, let's account for it and then exploit it.
I got a question, Jim.
Go ahead, Larry.
You already have a perfect antenna that is R is 50 and X is 0. So supposing we introduce we introduce either a minus value of X or a positive value of X, which a real antenna would show.
Yes, Larry, I deliberately chose a simple example, R50 and some reactants, to make this example simple and easy to understand, because I'm sure people's heads are hurting. But
okay,
yeah, if the R and X was over here, we would have to do something. Well, in a bad place. If it was here, we would have to do something with both admittance and a parallel network, and then in series with impedance or reactance in a series component. So this would be an L network.
No, I'm saying go back to the more complicated example. Okay. So make the load not or use the file I sent you, which has data from 3.5 to 4 megahertz.
Yeah, I was not able, in the time I had, Larry, I was not able to get that to load.
Okay. No, but I was going to say, let's say we introduce some value of X that's not 0 at the antenna. You can always change this. Down there. I don't know, make it inductive or something. I don't know. Okay. Now things start to change.
Yes.
And we don't have a 90-degree 75 ohm section, we've got a 180-degree section to see how that either screws things up or helps. Now the SWR is looking more like a real antenna.
Yeah, but it's not what we want. And
Yeah, exactly.
I thought I remembered from the article that it was a quarter wave. That's where the 90 degrees came from. But as I played with it, the 180 degrees it became clearer, and we could change that. And oh wow, SWR is a little higher, but flatter, still less than 1.5. My solid state amplifier will live with that all day. So those are the kind of machinations and things you can do with this software. And that is pretty much the point of this discussion, is things you could do with a Smith chart. Now, one other thing I will say, notice in my other example, I showed the polar plot, but one of the things you could do is show the rectangular plot, and you can specify what the horizontal axis is, and you can specify what the vertical axis is, okay? So, this can be gigahertz, and this can be ohms or furlongs or whatever, and you'll get a chart like this. You have both options, and then down here at the bottom, and I'm not going to get into it, but down here at the bottom, you have options of what to display, and where there's a line through it, you're not showing it, and where there's not a line through it, you're showing it. So this is really, really versatile. And whether or not you ever intend to use this, I would encourage you to download it, install it, and read the help file. It's 20-some pages. You will learn an awful lot about antennas and impedance matching. Anything else, Larry?
No.
Okay, thank you. Appreciate the input. Okay, so this is back to what we kind of just saw. Now, this chart is not from the Smith chart software. This chart is what the guy measured as he did what I talked about with the Smith chart software. And, in the real world, there are going to be some differences. But the bottom line here is across most of the 75-meter band, SWR is less than 1.5. I think we can all live with that. And at the very high end, it's only 2.0. And I suspect your manual tuner or the tuner in the radio can live with that. So that's the kind of techniques, that's the kind of things you can explore with this software. Any questions so far? Okay. So I talked about measuring impedance at the transmitter. Many of us have a device called a Rig Expert. There's also the Nano VNA. There's also, I have an old ancient MFJ device that I don't even know if it works anymore. And then I've got my fancy Hewlett-Packard network analyzer. But Rig Expert is pretty common, and I think there's enough of them in the club that we could, certainly if you want to measure something, I'd be willing to come out and put mine on it. Now, the interesting thing is, and this is another issue I've had conversation with on the software author, is Rig Expert stores the data in a binary format that SimSmith does not recognize. He can't figure it out. But with Rig Expert, you get a computer program, which I have on my laptop and my desktop, called Antscope, that will read that data, will also let you drive the Rig Expert, and then you can export that data to a comma separated variable file, CSV file, or an Excel file, which SimSmith can import. And the third bullet there is kind of important. Antscope can it can export in other formats as well. Read the manual carefully, and that manual is less than 20 pages. Um, and what I really like is the Rig Expert and Antscope software can give you both or either series and parallel resistance and reactance. And that is a useful capability because it means you don't need to do a conversion. If you want to do like an L network, um, with the first element being a shunt um, reactance. And a Rig Expert by itself, forget the Antscope software, although it'll do it too. The Rig Expert by itself can give you a Smith chart representation of your frequency sweep. Now, I would not use that on the Rig Expert to do impedance matching calculations. It gets too small, the resolution's too lousy, and my eyes are too bad. But I would import that into Antscope and then export the data. Well, first I'd import it into Antscope and use that to develop a strategy like I talked about here for developing the what the network is going to be. So if you've got a Rig Expert or has access to somebody like me with one that can come measure for you, there's a lot of opportunity here, and the SimSmith software will help you use that. The Rig Expert also allows you to calibrate it with what they call an OSL. That's an open short load. And that's a precise device that I have to calibrate my HP network analyzer. And it was several $1,000s new. I didn't pay anywhere near that. But if you prowl around, you can find them cheap. And if you can go into the Rig Expert and calibrate it with the OSL at the end of the feed line. Now the length of the feed line does not matter. What you see on a Rig Expert is the impedance at the end of the feed line. And the fancy guys call that the measurement plane. So those are just some miscellaneous notes on the Rig Expert. And I'm not trying to sell those things, but I love mine, and I found it very useful with the SimSmith software. So the conclusion, you could all ask me, do I really need to know this? And the most likely answer is probably not. But my hope is by exposing you to this helps you understand impedance and antenna matching and what's going on in the coax. I hope it might give you some ideas on measurements and optimizing your station single band antenna. A tuner can make the transmitter happy, but what's going on in the coax? And something I remember from when I was a kid is, yeah, a good tuner can load a bed spring. Doesn't mean it's going to radiate worth a hoot. And the example I alluded to earlier is my non-resident off-center fed dipole. It needs a tuner, period. It's not resident anywhere. But there's enough wire in the air that it radiates, and I hear in the last year or so, getting on the health and wellness net on 75 meters, I've been amazed at the people I can hear that others don't. And I have been very blessed to work the USS Midway Special Event Station in San Diego. Midway was my first ship as a Naval Academy midshipman in 1973. And more recently, I worked USS Alabama in Alabama in a crossband military. They were transmitting on a military frequency and listening on a ham frequency. But I need a tuner to make that work. And I acknowledge that I'm paying for additional loss in the coax. And I pay very, very close attention to what the tuner's doing before I go from 3 watts to 1500 watts. But there's an example of where this kind of understanding might be useful. In the long term, at the end of the day, I want to put up resident antennas for all EHF bands, but as Paul Wade, W1GHC likes to say, put something up and get on the air. Well, that's what I did with a non-resident dipole. I put something up based on the supports I had available. And again, why do you care? It would be nice to know what the antenna looks like. You know, when you measure at the end of the feed line, you're seeing the system, and that's nice to know. But it would be nice to know what's going on at the antenna, and then you can start developing an understanding of what's going on in the coax. So that's the point of this. I hope this is of value and not a waste of your time. A final aside, very much off subject, but something I wanted to share. I'll try to find a way to put this in the wash rag. As I was doing all the research for this, I ran across this program called SageMath that purports to be a free alternative to a whole lot of really expensive mathematics packages. We use one at work. I could never afford to buy it. Decades ago, I was given a bootleg copy of Mathematica. To buy it was tens of thousands of dollars. Now it comes free with a Raspberry Pi. I find that functionality to be most intriguing. One of the things that I find most useful is the ability to do the math and then graphing based on the math. And if I had found this sooner, some of the figures on this presentation might have been better, but you got what I could produce with the time I had, and I didn't want to kick it down the road any farther. So, okay, I'm done, boys and girls. Comments and questions, particularly comments. If this was a waste of your time, tell me. And most interested in questions, including those I will have to write down and go do some homework on and get back to you about.
Folks, you can either unmute your mics or write it in the chat session. Any questions?
Yeah, thank you. This was very interesting. I really enjoyed it. I wish I had this before I took my extra. I passed it, but this will help me a lot.
Okay. Yeah, Jim, we'd like to see the slide presentation at some point, or at least some of those. I took a couple of screen prints of a couple of the slides.
Yeah, okay. Can you hear me, Glenn?
Yes.
All right. I didn't see any questions I haven't already answered in the chat. And I do intend to get these slides to the webmaster, so they will be available on the website. And you know, most importantly, anybody has any questions or concerns about all of this, or wants help measuring or calculating or whatever, please don't shy about giving me a call. As you can tell, I'm a geek, and I enjoy doing this kind of stuff.
Do you have your chat window up there, Jim?
I do now.
Mark's asking a question.
I see. Are y'all recording?
No, further down. All the way down.
Thanks for all our articles and websites. Oh, what model of rig expert do you have? Okay, good question, Mark. I have the AA 1400 because I'm a microwave geek and I wanted to go up above 1296. I think they now have a 3 or 6 gigahertz version. The higher in frequency you go, the more expensive they are. I spent the money for the AA 1400 because I wanted to be able to use it at 1296 and 902 and so forth. If you're only interested in HF, they have a much cheaper version. And if you look carefully into their documentation, the really cheap versions won't do some of the things we've talked about. But if you go to the AA60 or AA100, they will give you features that you might want. And, if you want help if you want help deciding which one to go get, let me know what your functional requirements are, and I'll go prowl around their website and give you my opinion for whatever it's worth.
Okay.
Any other questions? All right, folks, I've taken way too much of your time. Thank you very much. I appreciate the attention. I hope that you found this of value. And like I said, I will get the slides posted. I don't know how soon, but I will get them posted on the WASH website. And I hope to see some of you at Two Rivers on Sunday.
And I will get this presentation posted up on my YouTube channel, and I'll send a link out through the Reflector. So if there's other people who would like to see it, they can see it there.
Yeah, please do send out a link on the Reflector, Glenn.
Will do.
All right, thanks. One more question on the chat.
Oh, well,
Michelle is asking you what your YouTube channel is, Glenn.
well, let me, Michelle, do you get the Reflector messages from WASH?
The East Coast Reflector?
No, from WASH.
No, I got this forwarded from Mike.
Okay.
Can I get on the mailing list?
Yes.
Yeah, I don't think we have anyone on here tonight who does that.
Michelle, send an email to W3WN. That's Ron.
W3WN?
Yeah, Whiskey 3, Whiskey November. And he will get you on the WASH Reflector.
And his email's on QRZ?
Yes. And as a backup, I'll send him an email as soon as I exit out of this.
Thank you.
I'll have to go find your email. But
there it is.
Oh, okay. Got it.
Thank you.
Let me see if I can copy. Yes, I did. Okay, I will send Ron an email, but it would probably be good if you send him one as well, as a backup.
Will do. Thank you.
All right. Thanks, everybody. Have a good night.
Thank you.
Thanks, Jim.
Thanks, Jim. Good night.
See y'all.
Thank you, Jim.
Thank
See
you,
ya.
Jim.
Oh, you're not talking.